Just realized now I didn't need to record. Okay, here we are. Guys, any questions? Afrika, Kwanele, Wendy. No, so okay. Maspierkus, Mshengu, Munu, Singalaka, Tabo, Stanton, Precious. Do we all get that? Okay. Sandile, guys, please, if you do not understand, you're free to ask a question. Any questions, guys? Okay, great. So just to show you some, to retalk this to you. And again, it says there an object immersed in a fluid is acted upon an upward force that arises because of pressures in a fluid. So fluids increase with depth, right? We have an upward force, which is the buoyant force, and the downward force, the gravitational force, right? So they're saying hence the upward force on the bottom of the object is more than the downward force, which is essentially talking to this over here, right? That's exactly the same. And the difference between the two, called the buoyant force, is equal to the weight of the object, and of the fluid's volume is the same as the object, right? This is Archimedes' principle. Then again, the buoyant force on a submerged object is equal to the weight of the object it displaces, right? Again, the weight of the fluid and okay. So now, what I want to show you now is whether things will sink or float. So we've talked about this together before, so we have an idea. So we have this cool image over here found on the internet, and this articulates what we just kind of what we're discussing, right? So there they're saying the buoyant force is equal to the weight of the displaced fluid, and always remember the buoyant force is given by the fluid. So if we have a positively buoyant force, and I'll describe this in the next slide, but just to explain, we that means the object will move upwards, right? That's like a cork, a wine cork if you drink wine. Where you look at the hood, for instance, another case, you put hood in the fluid, then what happens is you find it'll be also positive point. If you look between the two images there, you notice that the cork will be less immersed compared to the wood. Obviously, the wood is more dense. Whereas you have iron, right? We find you have negatively buoyant. That means it's sinking, right? So therefore the weight is more. And with the water, man, it's neutrally buoyant. So that means the weight and the buoyant force is essentially equal. That means it will be stable. Again, this is the principle used for ships on sea. Obviously, it has to be positively buoyant. And that's why when like if you watch the Titanic or any movie where water gets into the ship, we find it becomes negatively buoyant because the weight of the ship increases so much that the buoyant force can't keep it up. And obviously, the objective of a ship is that we want to keep a neutrally buoyant, not neutral, well, arguably positively buoyant or neutrally buoyant. Yeah. And again, with the submarine, same concept, right? That's all about manipulating the force of buoyancy. Okay, so how do we get this positively, negatively, and neutral? This is essentially due to this is just explaining what's happening here. So it's more about the densities. Okay, and so when the density of the object is less than the density of the fluid, right? So this is what's important here. We're going to find out that the buoyant force will be more, therefore it will be a positively buoyant, right? If you can see the B force is bigger, this is case A. Once again, the buoyancy force is equal to the density of the fluid, the volume displaced, right? It's of the object times the gravity, right? You'll see what I mean by that. However, if the density of the object is more than the fluid, what tends to happen? It will go down. So it's important to note that we're not talking mass, right? We're talking density. And the reason we talk density because liquids they occupy a volume. You know, they have no solid um, what's what I'm looking for um, structure, right? They occupy or they take form of whatever shape you put it in. So that's why we use density in this case. Okay. Um, and that's what it essentially is. And in the bottom, they have nicely there what's the net force. Essentially, if the buoyancy is bigger than the weight, you have rho fluid minus rho object times volume of the object times g. And obviously, I'll talk more about that. But I hope that's clear to everyone, right? I don't think that's difficult to understand whether something is buoyant or not. Um, okay, and then what's next is I think these are the two cases which they're referring to now in the book. Again, this is what it will look like. Um, and P is equal to rho fluid equals rho V fluid times G, which equals that. And essentially you find out that remember the buoyancy force is equal to the weight, and the weight is rho object, V object, G, and you can make them equal to each other, and therefore so you can play around with certain values. So I hope that's clear to everyone as well. And what's important here is that um, whether when an object is totally submerged or whether it's floating, right? Um, we must be cognizant of that, and we must always remember that we are looking at the the volume displaced by the fluid in V fluid, right? Whereas V object is the volume of the object. However, that that corresponds, and again, V fluid is the volume of the fluid displaced by the object. I wanted to be clear what V fluid is, and V object should be the volume of the actual object. Yeah, so that's basically it with the stuff, and we basically playing around with these formulas in different ways. But what's important to note when you immerse something, there's mg going down and there's b going up, and then yeah, you're gonna find certain things. So knowing this, I'm gonna open my whiteboard now, and I want you to try before I explain how to do it. Um, just looking at these formulas, okay? I'm gonna do the analysis, and I want you to actually plug in the values and solve. Okay, is there any questions before I move on? Is it clear as day, or is it dark as night? I'll give you guys 2 minutes to for absorption purposes. Guys, are there any questions? Please ask if you don't understand. Please, please, please. Any questions, guys? Any questions? Guys are quiet online, eh? I'll wait on any comments from you guys before I move on. I'm just comparing this. All right. So is the weight taken from the object or the fluid? Like I said, it's both. It's both. All right. It's both. If you look at the equation over there, and I'll show you what I mean by this. But V fluid corresponds to the volume displaced. Okay, so let me just quickly share the I'm just want to be careful with the volume of the object. Yeah, but the volume of the object is the actual volume of the object. Okay, right. So I'll just I'll do it again briefly. What I mean by this. So I'm gonna do the analysis, and then I want you to apply the analysis to this particular problem. Okay. So here we are. Need to book out. Just want to close some stuff here. All right. So again, looking at this, if you had an object, I'm going to just move to the side. This is my water. And I could have made my water blue. But okay. And we have an object displaced here, right? What you find is that we have two forces. We obviously know the weight. And we have the buoyant force, right? Which is exerted by the water. And what I'm saying is that forces up equals forces down. I'm sure you agree with me. We know that B will equal W. So what is B? B is rho fluid times the volume displaced, right, on V fluid times G. Again, this is just mass times gravity. That's force. You know what weight equals to force mg, right? And obviously mass is rho vg. I've mentioned this before. And when I say displaced, I mean this volume, right? Not the whole volume, just the volume displaced. Working on the other side of the equation, I'll make this color rather. This is rho of the object now. So the actual density of the object itself, right? Times the volume of the object. So not the displaced volume, but the total volume. I'm just being careful there. Times G. And once you have this relationship, you can essentially, you're playing around with what's happening here. Is it clear? Is it clear? I hope that's clear to everyone. Students, is that clear? So what is important here is just whether something's immersed and not immersed, right? So that's what you must be cognizant of. Whether something's immersed and not immersed. Because remember what I said, right? About when rho of the object is less than the rho of the fluid. Can just call it rho O, just for some simplicity purposes. And the rho fluid, and I mean by rho, I mean the densities. You find out it goes upwards, and when the density of the object is greater than the density of the fluid, it goes downwards, right? So this is the analysis, right? And then we apply the analysis to the particular problem. Okay, so in this question, and yeah, so let's see if you guys are able to figure out. So now again, this year we have an anchor. The anchor is completely immersed in the seawater, And our density over here, just by the way, is 7.8. 7.8 times 10 to the power 3. Okay. And so they're asking how much force is needed to support a 100 kilogram anchor when it's immersed in seawater. The density of the iron is 7.8 times 10 to the power 3. And the density of the seawater is 103 times 10 to the power 3. Okay, so what do you think the first thing would be? What should you do? So let's talk about the net force happening. Right? Someone tell me or type out what's happening with the net force. It must be equal to 0, I think. No, 0. Guys, look at the densities. Okay, so I'm going to help you here. So our density of our seawater is 1.03, right? Times 10 to the power 3. And the density of the anchor is 7.8. So the density is more of the anchor, right? How's the force is going to look? What's going to be a greater force? The weight, right? Is it not so? Let's think about this guy, right? It must be equal to 0, I think. Just think about this. What's more? So what we have here is mg minus b, right? In this case, right? The weight will be more. There's obviously a big amount of. None of you guys are getting this over here. Okay, so we basically want to sort out this equation. Okay, so we first want to find mg, and then we have to find b, right? So they give us the density, they give us the mass. I think that'll be easy. So we have mass times gravity already. Let me just, the mass times gravity we already have. So we know mg, or the weight. I should have called this weight over here. Guys, we're awfully quiet, eh? Awfully quiet. So that's 100 times 9.8. All right, you're going to get an answer. And for your buoyant force, it's going to be rho fluid. We need a volume of the fluid. And we're going to need G. Guys, are you seeing what's happening here? If you're lost, please say so. obviously using a snapshot of this picture, so it looks like this anchor is floating, but it's not, right? That's what's important here. B is the buoyant force. I mean, I don't know how you could even ask that. Guys, please ask questions if you're not seeing this. After this, you will, I mean, yeah, I mean, it's going to be over after today. So make sure you're grasping this. Okay, so can someone tell me what's the mass of this object? Or the weight, sorry. 980, thank you, Singalaka. So then we have the density of the fluid. How would we find the volume? Let's be smart about that. No, I didn't say that. I said B equals weight, isn't it? In this case, it's not. This is what I'm saying. In this case, it's not. This is when it's not. That's what I'm saying. It seemed I did not say it's rho GV, but that's what I'm saying. B is equal to, but it's not in this case. It's not floating, it's sinking. This is what I'm trying to articulate. Even though you're looking at that picture, you're thinking it's floating. It's not floating. It's moving. I hope that's clear. Yes. Even another picture looks like it's standing still, like it's floating, but we are looking at yes. But now, to find the volume, right, or the fluid displaced, we have to look at mass is rho V, and the mass that I'm talking about, Cabello, is that now we have to look at the volume of the anchor, and in this case, this is 7,800 times V, and let's get V. So because the reason why we're going to be using the total volume in this case is because the whole anchor is submerged, right? It's immersed. I know it's a bit strange. You'll get comfortable with it. You will eventually see what I'm talking about. Just bear with me. So let's find that volume, and this volume of the so-called object is the same volume as of the fluid. That's the amount of fluid displaced. I mean, due to the volume of the object. It sounds strange, but you will see. Yeah. So anyone can just get the volume of the object, or yeah, the volume of the object, which is the volume displaced by the fluid in this case. You'll see. No, don't worry. It just seems a bit strange now. All right, so I will get that volume for you, and that volume is 0.0128. Yeah, meters cubed. Okay, that's fine. Now I can see why everyone's confused, because obviously I'm not saying weight equals B, right? In that case, this whole thing would have been easy. There wouldn't have been a problem over here. But remember, the anchor has to sink. Okay. So that's what's happening here. That's due to the densities being different. Um, Not that the density is the only reason why it's going to float, but anyway. So once we have that, we can find the buoyant force now because we have the volume of the object, which is essentially the volume displaced by the fluid, because that's the whole volume immersed, right? So rho fluid is 1.03 times 10 to the power 3. We times that by 0.128. And again, you all get these questions, 0.00128 times 9.8. 9.8. All right, so just get B. Once you have B, you can find how much force is required to support the anchor. And that force obviously produced by the chain over there. We're gonna do more. We're gonna do more. You know, we do enough problems so we can get comfortable. I'm getting one so long for you. Okay, let's get that force quickly. Can I get that force, please? And I think I know what I'm missing here. I know what I'm missing here. Guys, what's the buoyant force? I think I know what I'm missing here. I should have said this is the weight, maybe. We've got the tension in that cable, which is the force we're looking for. And we also have the buoyancy force, right? Okay, so if I do this like this, just thinking maybe that's what you guys needed, we can see F plus B equals W, and therefore we have to solve now weight minus B. I hope this is clear. I think that's what's happening here. Maybe if I have it from that perspective, it's more easier. 850. Guys, did that help you a bit now? Because I'm done with, you should get around 850. That's correct. Yeah. 850 is fine. Okay, so just looking at different cases, you'll pick up how you have to solve these problems. Um, so can I give you one more like this, similar to this, and see if you're able to solve it. Okay, let me just. Okay. So it's the same setup as the previous one. Okay, but before I put this problem, this is the essential analysis you're gonna have to do, but there are two cases when an object is totally submerged and is a floating object, right? So it's in your textbook there, so I want you to just be aware. And when an object is floating, we make it equal to each other. right? It's like in equilibrium. In this case, it's not in equilibrium. I don't know if that's clear to everyone. So I think that the question would state whether it's floating or not. That's what I'm hoping for, at least. So I want you to try on your own now this one, using what you just did now. All right, can we do that? And the density of water is how much? You guys should know that by now. I'm not going to tell you. Can we quickly do that one? It's exactly the same as the previous one. Guys, are you happy? Can you? Is it clear? Is it clear, everyone? Okay, now it makes sense. Okay, let me just go back because I think it's always good to repeat something anyway. I'm going to put the question up now again. So, like I said to you, there are two cases. One when an object is totally submerged, and then you'll be using this analysis, right? This is what we essentially did, right? And depending on the density of the fluid, we can figure out what the net force is. In the previous question, our object was going downwards, right? So therefore our weight was more. So there was weight minus B, it's going downwards due to the density being more of the actual thing, right? Fully submerged. A floating object is when it's balanced, right? It's in equilibrium. I don't know what's other word I could look for, you know. Um, let me check the book, but it's essentially balanced. It's floating, right? It's floating nicely, and what we can do now is equate the two together. Is that clear to everyone? And that's when you can equate it quite nicely together. You see, now this is quite simple. When it's floating, is that clear to everyone? Thank you, Cabello, Charlie, and Lucizo is okay. Okay, same as the previous one. This is your turn. And please don't ask me what's the tension of water. You should know that. Okay, carry on. I'll give you guys 5 minutes. Are you guys winning? It's 11 o'clock now. You guys get the answer? You guys get the answer? The answer should be 0.145 newtons. You guys get the answer? Fantastic. That means you're definitely on the right track. Okay, great, guys. Anyone else? Okay. I'm going to give you some homework, but I'm just looking at some problems. I'm going to the college physics textbook and we're going to do a floating example now, right? So you must just always be cognizant of whether the thing is floating or not floating. And we can briefly touch on that example when I see you again. Thanks. Okay. So that's the answer for B, but A's answer is, I'll give it to you now. Just give me a second. No, there. Can someone write the volume for me there so long while I get that answer? My CPU is high again. Just give me a second. The volume is what was that again? Oh, just give me a second. The volume is what's the rest? The volume is 9.26 times 10 to the power negative 6. V is 9.26 times 10. Yeah. Meters cubed. Negative 6, sorry. Yeah, that's the volume. Yep. No, I'm not going to do that. You can do that yourself. You can ask your mates to help you. It's easy. If you can't do it, I can touch it on Monday again. But it's if you apply the same principles, you should be fine. All right, so let's see what happens when something floats now. And this is when it's more easy. Okay. So sometimes it doesn't state that. That's a bit of my problem. but you're gonna have to obviously really interpret the question nicely. So yeah, okay. So remember, typically when it's fully submerged, that is when we have this change, this difference in forces. When it's fully submerged, that's debatable. And when it's floating or when it's partially submerged, this is when we make the forces equal to each other. So I'll say that again. Typically, when it's totally submerged, we look at the densities, and when it's partially submerged, and then we can obviously just equate the two together. I hope that's clear to everyone. So make sure you solve that. I'm sure you guys can figure that out. All right. So in this case, Cabello, this one is for you in terms of the densities. Here we have a raft, piece of wood, and they give us the surface area, and they give us its volume. And when the raft is placed in fresh water, to what depth is the raft being submerged, right? In this case, we're floating. So I'll just have my raft over here. And in this case, we have the weight going down, and that equals the buoyant force. Okay, straightforward problem. And now, because it's in equilibrium, so some of the force in the y direction, right? We're applying always this. So you don't want to be fancy. We know that it's going to be B minus W equals that. Therefore, we know B equals W. So can you see, or submerged, floating, we're able to equate the two. Is that clear to everyone? Can you see the difference between the two? I hope you guys can see the difference between the two cases we just did now. Can we see the difference? Okay, yeah. So fully submerged, partially submerged, right? But I mean, I'm not an expert in buoyancy, but one must also be careful. So here, you will solve it for me as normal, but we know B equals W, so it's rho of the fluid. And remember, this is the volume of the displaced fluid. This is G, this is rho of the object, and this is the volume of the object. So remember, this is displaced, right? Displaced, very important. So displaced meaning it's this area here. Right, that area there. The volume of the object is the whole volume of the object, and times G. So we need to find H. And what is volume equal to typically? That's going to be your area times your height. Is it not so? Afrika, do you agree with me, Ms. Bierkes? You see that? All right. Fantastic. Okay, solve for me for that H. Did I solve it? Mfuno's got it. Nope, that's not right. You're missing something. All right. I hope you guys have solved it. So here we have water, 1000. The volume displaced is that section, but we know its surface area, which is 5.7, times that by h, because um, we don't know how much has been immersed by. We have g, but in g's, we just cancel the g's because we have g's on both ends. The object's density is 600, right? And the total volume of the object is 0.6 as given here. And all we have to do is solve for h. Quite simple. And h, you should get around 0.0632 meters. So from what I can tell, this doesn't typically happen, this problem. They don't like this easier one. But yeah, it's obviously worth noting. Yes, fantastic, Cabello and Afika. Okay, so what I'm gonna do now is give you one to play with, and then we'll touch on it and I see you again. Um, and then yeah, I'll continue the next section. So guys, I recommend practicing, obviously, um, and yeah, keep the academic blood flowing through the brain. It's not too difficult. So yeah, let me just hold that problem for you, and then you can take a picture, but I will put it on Blackboard, and I'll Fika will remind me. So I like this one. Just gonna place it now. So let's see if you're able to conduct the analysis on this one. So over here, that's the problem. I'll just park it here. Just take a picture of it. At A, I like this one a lot. It's floating, right? So just like we just did now. And then at B, obviously, it's gonna sink. So you have to know how the densities and stuff work. Okay. So do we again the density of water? It's there somewhere. Um, that's all you basically need. It's 1,000 kilograms is per normal, but on the sea we're smart with the forces. on the CV Smart with the forces. Now, yeah, so it's, oh, the volume is given there as well, so you can find the density. Okay, so the first one, it's floating. Obviously, it's sinking. You have to understand how the forces go when it sinks. What is more? What is less? Yeah, and I think you can treat the F weight FWB is basically like a tension or the normal force or the additional force acting. Okay, so guys, I'll see you on Monday. Most probably on campus. You'll do this problem and then you'll do fluid flow. Okay then. All the best. I'll see you guys on Monday. Cheers, guys.